Why doesn't the moon spin? It's a question so simple it feels almost childish, and yet hidden beneath that still pale glow is one of the quietest, most elegant mysteries in the cosmos. Tonight, as you drift into rest, let your mind rise slowly above the turning earth. Imagine the moon hanging there, motionless, serene, like a lantern pinned to the sky, a world that never changes its face and yet is never truly still. Because behind that calm expression lies a story shaped by fire, gravity and time, a cosmic rhythm billions of years in the making. A rhythm so perfect that it appears frozen, but only to eyes that watch too quickly. In this gentle journey, we'll explore why the moon seems to refuse its spin, how an ancient gravitational embrace sculpted its stillness, and why that quiet balance matters for every tide, every season, and even for life itself. So breathe slowly, settle into the dark, and let the universe move around you in soft, steady motion. If you find comfort in these gentle cosmic stories, a light tap on like and subscribe helps this small channel reach others searching for a peaceful night. And now, let the quiet pull of gravity guide you into the story. Welcome to Sleepy Science Stories. Part 1. If the moon does not spin, why do we only see one face? The moon does not spin, or at least, that is what most of us have come to believe when we gaze upward on clear evenings. For every night of our lives, from childhood wonder to adult contemplation, we have looked up toward that glowing disk suspended in the darkness and seen the same familiar face staring back at us. The same shadows stretched across its surface, the same ancient craters marking its skin like memories carved in grey stone, the same silent expression that has watched over humanity since before we had words to describe what we were seeing. But what if I were to tell you, in this quiet moment, that this apparent stillness is actually an illusion? Not a deception, but rather one of the most precise and intricate dances occurring anywhere in our solar system. A performance so perfectly timed that it appears to our eyes as if no movement exists at all. Let us begin with a fundamental fact, one that may seem contradictory at first. The moon does indeed rotate. It spins on its axis just as Earth does, just as nearly every celestial body in our cosmic neighborhood does. But here is where the extraordinary precision reveals itself. The moon rotates in perfect synchrony with its orbit around Earth, turning exactly the rate needed to keep one hemisphere perpetually facing toward us. This remarkable condition, this cosmic coincidence that is not really a coincidence at all, is what scientists call tidal locking, and it is neither magic nor chance. It is physics, pure and simple, shaped gradually by time measured in billions of years, by gravity stretching across space, and by friction working slowly but inexorably inside the moon itself. According to detailed data collected by NASA's Lunar Reconnaissance Orbiter, a spacecraft that has mapped our moon with extraordinary precision, the moon completes exactly one full rotation on its axis every 27.3 days. That is precisely the same amount of time, down to the hour, that it takes for the moon to complete one full orbit around Earth. Think about that for a moment. The moon's day, the time it takes to spin once, equals exactly the length of its year, the time it takes to circle our planet. That is why, from our perspective here on Earth, it appears as though the moon never turns at all. But in reality, beneath that apparent stillness, it is spinning at just the right rate, turning with just the right speed to keep one single hemisphere facing us at all times. To truly understand this strange and beautiful synchronization, imagine for a moment that Earth and the moon are connected not by empty space, but by invisible threads of gravity reaching across the void and binding them together in an eternal embrace. Early in the moon's history, roughly 4.5 billion years ago, shortly after it likely formed from the scattered debris of a massive collision between Earth and a protoplanet that scientists have named Theia, the moon rotated much, much faster than it does today. Each lunar day back then might have lasted only a few hours, perhaps even less. The young moon spun rapidly, a blur of motion in the early solar system. But as the eons passed, as millions upon millions of years accumulated into billions, Earth's gravitational pull began to work its subtle magic. It distorted the moon slightly, gradually stretching it into a shape that was no longer perfectly round, no longer a true sphere. This tiny bulge, this slight deviation from perfect symmetry, created something called tidal friction within the moon's interior. This friction acted like a cosmic brake, a drag on the moon's rotation that persisted day after day, year after year, millennium after millennium. Slowly, imperceptibly, to any observer who might have been watching, the rotation began to slow down. It decelerated gradually until finally, at one precise moment in time, it matched perfectly with the moon's orbital period around Earth. At that exact instant, the locking became complete. From that moment forward, spanning the remaining billions of years of the moon's existence, only one face would ever look back at us. One hemisphere would be forever Earthward, forever observing our blue planet hanging in its sky. The other hemisphere would remain hidden, unknown, mysterious until human technology finally allowed us to glimpse it. NASA scientists who study these phenomena with great care and precision call this state synchronous rotation. It represents a delicate balance, an equilibrium point where angular velocity, which describes the speed at which the moon spins on its axis, becomes exactly equal to orbital velocity, which describes the speed at which the moon travels around Earth in its elliptical path. The result of this balance is truly mesmerizing when you pause to consider it. As the moon orbits our planet, traveling through space at more than 3,000 kilometers per hour, it turns just enough, rotates just precisely to keep one side eternally fixed toward us. It is like watching a dancer who never looks away from her partner, who spins in perfect time with their shared movement, maintaining eye contact through every step, every turn, every moment of the performance. We can test this mathematically. We can verify it with numbers. The moon's average orbital speed is approximately 1 kilometer per second, a velocity that seems almost leisurely compared to the speeds at which planets orbit the sun, but which is still far faster than anything we experience in our daily lives. Meanwhile, its rotation period of 27.3 Earth days means its spin rate is roughly 0.037 degrees per hour. That is extraordinarily slow when you really think about it. It is so slow that it would take a full month for the moon to complete one single turn on its axis, one complete rotation from any given starting point back to that same orientation. This near-perfect alignment, this synchronous lock, is not unique in the cosmos. It is not something special that only our moon has achieved. Many moons throughout our solar system share this same fate, this same locked orientation with their parent worlds. Jupiter's volcanic moon, Io, shows only one face to its giant planet. Saturn's hazy moon, Titan, keeps one hemisphere eternally facing the ringed world. Even distant Pluto and its companion Charon are mutually locked, each showing only one face to the other, spinning and orbiting in perfect harmony. But Earth's moon holds a special place in this cosmic catalogue because of how precisely it achieved this balance, despite its unusually large size relative to Earth. Our moon is proportionally one of the largest satellites in the solar system, and yet it has found this perfect equilibrium, this point of ultimate stability. If you have ever looked at the moon through a telescope, perhaps on a clear night when the atmosphere was steady and the seeing was good, and if you noticed small changes at its edges over time, subtle shifts in what features were visible along the limb, then you have glimpsed a phenomenon that astronomers call libration. This is a gentle oscillation, a slight wobbling motion caused by the moon's orbit not being perfectly circular, but rather slightly elliptical, and by the moon's axis of rotation being tilted just a bit relative to its orbital plane. Thanks to libration, to this slight wobbling and tilting, we can actually observe about 59% of the moon's total surface from Earth over time. Even though at any single moment it seems we only ever see precisely half, over the course of weeks and months, as we watch carefully, slightly more than half becomes visible. It is a subtle reminder, delicate but persistent, that even in apparent stillness there exists motion. Even in what seems frozen, there is gentle movement. scientists have studied tidal locking not only through mathematical models and theoretical calculations, but also through direct observation and measurement. Data from NASA's Gravity Recovery and Interior Laboratory mission, known by its acronym GRAL, which carefully mapped the Moon's gravitational field with extraordinary precision, revealed variations in gravity that match perfectly with models of internal heating and tidal deformation. These measurements confirm that the locking process is not merely theoretical speculation or mathematical convenience. It is written into the very rock of the Moon itself, recorded in its structure. Fractures running through the lunar crust, stress lines visible in the patterns of Maria and highlands, variations in crust thickness from one region to another. All of these features point toward billions of years of gravitational stretching, of tidal forces working patiently to reshape the Moon. Dr. James Williams, a scientist at NASA's Jet Propulsion Laboratory who has spent years studying the dynamics of the Earth-Moon system, once described this phenomenon in beautifully simple terms. He said that tidal locking is nature's way of achieving stability through loss. In other words, as the Moon gradually lost rotational energy over cosmic time, dissipating that energy as heat through internal friction, it simultaneously gained something perhaps even more valuable. It gained harmony. It reached a stable orbit and rotation rate that have lasted for billions of years, that will persist for billions more, representing one of the most enduring relationships in our solar system. But let us make this tangible. Let us bring it down from abstraction to something we can visualize. Imagine for a moment that you are standing on the Moon's near side, the hemisphere that eternally faces Earth, the side marked by the dark Maria that form patterns we have named the man in the moon or the rabbit, depending on cultural tradition. You are standing there in your spacesuit, boots pressed against the ancient regolith, and you look up. There, hanging in the black sky above you, is Earth. That beautiful blue and white marble, swirled with clouds, gleaming with oceans, marked by the brown and green of continents. And here is the remarkable thing, that Earth does not move. It never rises above the horizon. It never sets below it. It simply hovers there in the sky, perfectly still, fixed in position, while the stars drift slowly around it over the course of days and weeks. That is what tidal locking means in practice, in lived experience. It means an eternal view of home, unchanging, constant. But now imagine you walk to the far side of the Moon, the hemisphere we never see from Earth, the side that remains forever hidden from our gaze. You make that journey across craters and mountains, across the lunar surface, and you look up again. And there in the sky you see nothing. Earth never appears. The sky there is utterly empty of the planet that created the Moon's fate, that shaped its destiny through gravity alone. There is something haunting about that symmetry, something that touches the edge of loneliness, one side in eternal view, one side in eternal separation. Scientists measure this phenomenon in terms of angular momentum and energy dissipation, in equations and graphs and numerical models. But emotionally, philosophically, it represents perhaps the closest thing to cosmic stillness that we know. Every crater on the near side, every ridge and mountain peak, every boulder and grain of dust has faced our planet for billions of years. They have all weathered the impacts of meteorites while silently reflecting sunlight back to us, creating the gentle glow we call moonlight. Meanwhile, the far side, which is rougher in terrain, older in some regions, more heavily scarred by ancient impacts, lives in perpetual shadow from our gaze. It remains mysterious, less explored, less understood. This perfect alignment between rotation and orbit has also shaped life on Earth itself in ways that are subtle but absolutely profound. The Moon's gravitational pull, working across the space between our two worlds, creates the ocean tides that rise and fall twice each day. These tides have shaped coastlines, influenced marine life, affected human settlement patterns. The Moon also helps to stabilize Earth's axial tilt, preventing wild oscillations that would make our climate far more chaotic. And the Moon's gravity gradually slows Earth's rotation over time, making our days incrementally longer with each passing century. Without this gravitational balance, without this locked dance between Earth and Moon, our days might be significantly shorter, our seasons might swing more erratically, and the climate might be far less stable and predictable. Life as we know it might never have evolved, or might have taken radically different forms. So while it might initially seem like the moon's lack of spin, or rather its perfectly synchronized spin, is nothing more than a trivial curiosity, something interesting but ultimately unimportant, it is actually part of the deep reason why Earth's environment has remained so friendly to life for billions of years. As Neil deGrasse Tyson, the eloquent astrophysicist and science communicator, once observed, the moon is not merely a companion to Earth, not just a satellite orbiting nearby. It is a stabilizer, a cosmic anchor, something that makes Earth a comfortable and consistent home for living things. To the human eye, untrained in astronomy, simply gazing upward on a quiet evening, the moon's stillness feels peaceful, serene, calming. It seems like a fixed point in an ever-changing sky. But to the scientist's eye, trained to see beyond the surface, educated in the language of physics and mathematics, that apparent stillness is actually a record of motions gradually slowed to absolute perfection. And that is precisely what makes this mystery, this puzzle of why the moon does not appear to spin, so utterly captivating. The illusion of immobility is, in truth, the most elegant movement of all. It is motion perfected, motion refined, motion brought to its ultimate expression of balance. So the next time you step outside on a clear night and see that pale disk glowing softly in the darkness above, perhaps just after sunset when the first stars are emerging, remember this truth. It is not frozen. It is not still. It is dancing in perfect silence, spinning and orbiting at precisely the same time, moving in a rhythm so fine-tuned by gravity itself over billions of years that it appears to our eyes as motionless. That is not stillness. That is perfection. In the next part of our journey together, we will venture deeper into that invisible force, into the tidal grip that keeps the moon locked forever in this embrace, transforming what might have been just an ordinary rocky satellite into one of the most precise mechanical systems anywhere in the cosmos. The force that makes this possible is gravity, ancient and patient, and its story is extraordinary. Part 2. What invisible force keeps the moon locked forever? There is no magic operating in the sky above us, despite what ancient peoples might have believed when they gazed upward and tried to make sense of celestial movements. There is only gravity, relentless in its action, ancient beyond imagining, patient beyond comprehension. Gravity does not roar like thunder. It does not flash like lightning. It does not announce itself with drama or spectacle. Yet for 4.5 billion years, spanning the entire history of our solar system, from its violent birth to its present maturity, this invisible force has bent worlds to its will, has shaped their motion through space, has slowed their spin through friction, and has held them in perfect balance against the chaos that might otherwise reign. The moon, our constant companion, is one of gravity's quietest victims. Or perhaps we should think of it differently. Perhaps the moon is one of gravity's most perfect creations, a masterpiece of slow sculpting across cosmic time. To truly understand why the moon remains locked in its eternal embrace with Earth, why it can never turn away despite the vast emptiness of space that might seem to offer freedom, we must journey back to the fundamental equations that describe nearly everything that moves in our universe. We must examine Newton's law of gravitation, that elegant mathematical statement that revolutionized our understanding of nature. And we must explore Kepler's laws of orbital motion, those 3 simple rules that describe how planets and moons trace their paths through space. Isaac Newton, working in the 17th century with nothing more than pen and paper, mathematical insight and careful observation, showed us something profound about the universe. He demonstrated that every mass, every single object that has substance and form, attracts every other mass. The force between any 2 bodies, whether we are talking about Earth and the Moon, the Sun and a distant comet, or even 2 pebbles lying side by side on the ground, depends on 2 things. It depends on the masses of those objects, how much matter they contain, and it depends on the square of the distance between them, how far apart they are separated in space. The mathematical formula that expresses this relationship looks deceptively simple when you first encounter it. The force equals the gravitational constant multiplied by the product of the two masses divided by the distance between them squared. Written in symbols, it appears elegant, compact, almost beautiful in its simplicity. But hidden inside that equation, encoded in that relationship between mass and distance, is a story of energy exchange that spans cosmic time, that operates over billions of years, that gradually but inevitably transforms the way celestial bodies move and spin. When the moon first formed, likely from the debris ejected when a Mars-sized protoplanet struck the young Earth in a cataclysmic collision, it was spinning much faster than it does today. That ancient moon, newly formed and still glowing with the heat of its creation, completed rotations that might have lasted only a few hours, perhaps even less. That means its surface was moving at hundreds of meters per second relative to its center, racing through space, spinning freely. But Earth's gravitational pull, reaching across the space between the two newly formed worlds, did not simply tug on the moon as a whole. Gravity does not work that way. It is not a uniform force applied equally to every part of an object. Instead, gravity stretched the moon, pulling more strongly on the side facing Earth than on the far side, creating what scientists call a tidal bulge. This stretching, this deformation, created small irregularities in the moon's shape. One bulge formed facing Earth, drawn outward by stronger gravitational attraction. Another bulge formed on the opposite side, created by the inertia of material being pulled less strongly. These bulges were not huge, not dramatic mountains of rock reaching toward Earth. They were subtle, perhaps only a few meters high initially, gentle undulations in the moon's surface, but they were enough. They were sufficient to begin a process that would continue for billions of years. As the moon continued spinning rapidly, faster than it orbited Earth, these tidal bulges tried to rotate along with the rest of the moon. But Earth's gravity worked constantly to pull them back into alignment, to keep them facing toward and away from Earth. This created friction inside the moon as rock flexed and moved, as internal layers slid past one another, as material heated up from the constant deformation. That friction dissipated energy. It converted the moon's rotational energy, the kinetic energy of its spin, into heat that radiated away into space and was lost forever. With each passing day, with each orbit, with each rotation, the moon spun just slightly slower. The loss of energy was tiny on any given day, unmeasurable across a human lifetime or even across thousands of human lifetimes. But time in the cosmos is measured differently than human time. 1,000,000 years is nothing in the life of a world. 1,000,000,000 years is a reasonable timescale. And over those vast stretches of time, the cumulative effect was dramatic. The moon's rotation gradually, inexorably slowed down. This process continued relentlessly until a special moment arrived. The moon's rotational period, the time it took to spin once on its axis, became exactly equal to its orbital period, the time it took to circle Earth once. At that precise instant, the tidal bulges aligned perfectly with the Earth-Moon line. They no longer needed to rotate to stay aligned. The friction stopped, the energy loss ceased, equilibrium had been reached. From that moment forward, spanning the remaining billions of years up to our present day, and continuing into the distant future, the moon would remain locked, showing only one face to Earth forever. Mathematically, we can describe this using the concept of tidal torque. Torque is simply a rotational force, a twisting action that changes how fast something spins. Earth's gravity creates a torque on the moon's tidal bulge whenever that bulge is not perfectly aligned with the line connecting the centers of the two bodies. The magnitude of this torque depends on several factors. It depends on how massive Earth is, on how large the tidal bulge is, and on how misaligned it is from the Earth-Moon direction. The formula involves terms for gravitational constant, the masses involved, the separation distance, and the size of the deformation. When worked through carefully, these equations tell us exactly how the moon's spin changes over time. NASA scientists studying tidal evolution have run detailed computer simulations of this process. They start with a rapidly spinning young moon, input the known masses and distances, apply the equations of tidal torque, and let the simulation run forward through billions of years of virtual time. Every time they do this, regardless of exactly what initial rotation rate they choose, the result is the same. The moon slows down, it locks, it reaches the stable state we observe today. The mathematics does not lie. The physics is inexorable. One of the most beautiful confirmations of this theory comes from lunar laser ranging experiments. Beginning in 1969, when Apollo 11 astronauts placed the first retroreflector array on the moon's surface, scientists have been bouncing laser beams off the moon and measuring, with extraordinary precision, exactly how far away it is at any given moment. These measurements, conducted continuously for more than 50 years now, confirm that the moon is gradually moving away from Earth at about 3.8 centimeters per year. This recession is happening because tidal forces are still at work, still transferring angular momentum from Earth's rotation to the moon's orbit, gradually pushing it farther into space, while simultaneously slowing Earth's rotation. The fact that this process is still ongoing, that energy is still being exchanged even though the moon is locked, tells us something important. The locking is not the end of the story, it is merely one chapter. The full tidal evolution of the Earth-Moon system continues, will continue for billions of years into the future, until perhaps both bodies become mutually locked to each other, until even Earth's rotation slows to match the moon's orbital period. But that is a story for later. What matters right now, in this moment of our exploration, is understanding that the moon's locked rotation is not arbitrary, it is not coincidence. It is the inevitable result of gravity operating over cosmic time, of energy being dissipated through friction, of mathematics playing out in the motion of worlds. Every tidally locked moon in our solar system tells the same story. Io orbiting Jupiter, Titan circling Saturn, Europa and Ganymede and Callisto, all the major satellites of the giant planets. They are all locked because they all experience the same process, the same slow grinding down of spin until equilibrium was reached. Dr. James Williams of the Jet Propulsion Laboratory, whom we heard from earlier, has described tidal locking as one of the most common outcomes in the solar system for satellites orbiting close to their parent planets. The closer a moon is to its planet, he explains, the stronger the tidal forces become, and the faster the locking occurs. Very close moons might lock within just millions of years. Distant moons might take billions of years, or might never fully lock if their orbits are too far and tidal forces too weak. Our moon, orbiting at its current distance of roughly 384,000 kilometers, locked relatively quickly in cosmic terms, probably within the first few 100 million years of its existence. The gravitational force responsible for all of this follows an inverse square law. That means if you double the distance between two objects, the gravitational force between them drops to 1/4 of what it was. If you triple the distance, it drops to 1/9. This rapid fall-off with distance is why tidal forces are so strongly dependent on separation. The difference in gravitational pull between the near side and far side of the moon is what creates the tidal bulge, and that difference gets smaller as the moon moves farther away. This is part of why the moon's recession is gradually slowing. As it moves farther from Earth, tidal forces weaken, the torque decreases, and the rate of energy transfer slows. But even slowed, even weakened, the process continues. It has not stopped. Every high tide on Earth, every low tide, every movement of water responding to the moon's gravity represents energy being dissipated. The friction of water moving against coastlines, the flexing of the solid Earth beneath the oceans, all of this converts kinetic energy into heat. That energy has to come from somewhere. It comes from Earth's rotation. Our planet is spinning slower today than it was yesterday, though the difference is far too small to measure directly. Over a century, Earth's day lengthens by about 1.7 milliseconds. That seems tiny, insignificant. But over millions of years, it adds up. In the Devonian period, about 400 million years ago, Earth's day was only about 22 hours long. Ancient corals from that time, which laid down growth rings that can still be counted today, show evidence of more days per year than we have now. The year itself has not changed in length. Earth's orbit around the Sun remains stable. But the rotation period, has been steadily increasing. The Moon is responsible for most of that change. Gravity, then, is not just a force that holds things together or keeps planets in orbit. It is an active sculptor working across time to reshape how things move and spin. The Moon's locked rotation is just one example of its handiwork, one demonstration of its patient, invisible power. There is something almost poetic about it when you pause to consider it deeply. The same force that makes an apple fall from a tree, that keeps our feet firmly on the ground, that holds the atmosphere close to Earth's surface, also reaches across hundreds of thousands of kilometers of empty space to grab hold of another world and slow its spin until it matches its orbit perfectly. Newton himself probably never imagined the full implications of his law of gravitation. He discovered the mathematical relationship, wrote down the equation, used it to explain the motions of planets and moons and comets. But could he have conceived that this same law, operating over billions of years, would gradually lock satellites into synchronous rotation? Could he have imagined that his equation would explain why future observers would always see the same face of the Moon? Perhaps, perhaps not. But the mathematics cares nothing for what Newton imagined. The physics operates regardless of our understanding. The Moon locks because gravity demands it. And so we come to appreciate that what keeps the Moon locked forever is neither mystery nor magic, neither divine intervention nor cosmic coincidence. It is simply gravity, working as it always has, as it always will, pulling, stretching, creating friction, dissipating energy, driving systems toward equilibrium. In the next part of our journey, we will explore how scientists measure these forces, how we know with such certainty and precision what is happening between Earth and Moon, how laser beams and ancient mathematics combine to reveal the secrets of tidal locking. The invisible becomes visible through careful observation and mathematical reasoning. The silent dance of worlds can be heard if we know how to listen. Part 3. How do scientists measure tidal forces acting on the Moon? To understand something invisible requires tools that can make it visible. To measure something as subtle as tidal forces acting across hundreds of thousands of kilometers of space requires precision that pushes the boundaries of what technology can achieve. Yet modern science has accomplished exactly this. We can now measure the forces between Earth and Moon with extraordinary accuracy, can track the Moon's position to within millimeters, can detect changes in its orbit that happen over years and decades. This is not guesswork or theoretical speculation. This is direct measurement, hard data, collected patiently over many years. The primary tool for measuring the Earth-Moon distance, and thereby understanding tidal evolution, is a technique called lunar laser ranging. It sounds like something from science fiction, but it has been operational since July of 1969, when the Apollo 11 astronauts placed the first retroreflector array on the Moon's surface during humanity's first landing on another world. A retroreflector is a special type of mirror consisting of small corner-cube prisms that reflect light directly back toward its source, regardless of the angle at which the light arrives. These retroreflectors are still there today, sitting quietly on the lunar surface, along with additional arrays placed by Apollo 14, Apollo 15, and 2 Soviet Lunokhod rovers. The principle behind lunar laser ranging is elegant in its simplicity. Scientists at observatories on Earth point powerful laser beams toward the Moon, specifically targeting the known locations of these retroreflector arrays. The laser pulse travels through space at the speed of light, roughly 300,000 kilometers per second. It reaches the Moon's surface, strikes the retroreflector, and bounces back toward Earth. The same observatories that sent the pulse now detect the returning photons, usually just a handful of them from the trillions that were initially transmitted. By measuring the total time elapsed between sending the pulse and receiving the reflection, typically measured in seconds, scientists can calculate the precise distance to the Moon using the simple relationship that distance equals speed times time. Because we know the speed of light extremely accurately, and because we can measure time intervals with extraordinary precision using atomic clocks, the calculated distance is remarkably accurate. Modern lunar laser ranging measurements can determine the Earth-Moon distance to within about 1 millimeter. Think about that. 1 millimeter precision across nearly 400,000 kilometers of space. It is like measuring the distance from New York to Los Angeles to within a fraction of the width of a human hair. Over the 50-plus years that these measurements have been collected, astronomers have accumulated an enormous database of lunar distance measurements. By analysing how these distances change over time, tracking patterns that emerge across years and decades, they can detect the Moon's gradual recession. The data clearly shows that the Moon is moving away from Earth at approximately 3.8 centimeters per year. That is about the rate at which human fingernails grow, a tiny amount in any single year, but substantial when accumulated over millions or billions of years. This measured recession rate allows scientists to calculate the rate at which tidal energy is being dissipated in the Earth-Moon system. The equations connecting orbital change to energy loss are well understood, derived from basic principles of physics and orbital mechanics. When you plug in the observed recession rate, the known masses of Earth and Moon, and the current orbital parameters, you can calculate that approximately 3.7 terawatts of power are currently being dissipated through tidal friction. Most of that energy loss occurs in Earth's oceans and solid body, where the movement of tides against the planet's surface creates friction and generates heat. 3.7 terawatts is an enormous amount of power. To put it in perspective, it is roughly equivalent to the total power consumption of all human civilization. All of our cities, factories, vehicles, computers, lights, everything we power with electricity and fuel, amounts to about the same energy that is being continuously dissipated through tidal friction between Earth and Moon. That energy has to come from somewhere, and it comes from the rotational and orbital energy of the Earth-Moon system itself. Over time, this energy loss is why Earth's rotation slows and why the Moon gradually recedes. But lunar laser ranging is not the only technique scientists use to study tidal forces and the Moon's motion. Another powerful method involves studying the Moon's internal structure through its gravitational field. NASA's Grail mission, which operated from 2011 to 2012, used two identical spacecraft flying in formation around the Moon to map its gravitational field with unprecedented precision. The basic idea was beautifully simple. As the two spacecraft orbited the Moon, maintaining formation with one another, any local variations in the Moon's gravity would cause tiny changes in the distance between them. By measuring these distance changes using microwave signals bounced between the spacecraft and tracking how those changes correlated with position over the lunar surface, scientists could construct a detailed map showing where the Moon's gravity is slightly stronger or slightly weaker. These variations in gravity reveal information about the Moon's internal structure. Regions with higher density pull more strongly. Regions with lower density pull more weakly. Mountains and surface features create small gravitational signals. But more importantly for our story, the overall shape of the Moon's gravitational field reveals the tidal bulge that has been frozen into its structure. The Moon is not perfectly spherical. It is slightly elongated along the Earth-Moon line, stretched out by billions of years of tidal forces. This elongation creates a permanent gravitational signature, a fingerprint of the tidal locking process itself. The Grail data confirmed theoretical predictions about how tidal forces should have deformed the Moon over its history. The measurements matched the models. The Moon's shape is exactly what you would expect from a body that has been tidally locked for billions of years, that has been stretched by Earth's gravity and has frozen into that elongated shape. This is powerful evidence that our understanding of tidal locking is correct, that the physics we use to explain it is accurate. Scientists also study ancient geological features on the Moon's surface to understand its tidal history. Certain patterns of fractures, called graben, are long, narrow trenches formed when the lunar crust was pulled apart by internal stresses. Some of these fractures align in ways that suggest they were created by tidal forces acting early in the Moon's history when it was still cooling and contracting. The orientation of these features, their distribution across the lunar surface, and their relationship to other geological structures all provide clues about how tidal forces shaped the moon's evolution. Another line of evidence comes from studying the moon's shape more broadly using topographic data. Missions like the Lunar Reconnaissance Orbiter have mapped the moon's surface elevation with extraordinary detail, measuring the heights of mountains, the depths of craters, the subtle undulations of maria and highlands. When this topographic data is analysed carefully, it reveals that the moon's shape deviates from a perfect sphere in very specific ways. It is slightly elongated along the Earth-Moon axis. It has a slight bulge toward Earth and a corresponding bulge on the far side. These are the tidal bulges we have been discussing, frozen into the moon's solid rock. The magnitude of these bulges, measured in the topographic data and confirmed by the gravitational data, allows scientists to calculate how much energy was dissipated during the moon's tidal evolution. By working backwards from the current frozen bulges, using models of how rock behaves under stress over long time periods, researchers can estimate how much tidal heating occurred inside the moon, how much energy was converted to heat through friction, and therefore how much the moon's rotation must have slowed over time. All the numbers are consistent. The measurements match the theory. The evidence from multiple independent sources all points to the same conclusion. Perhaps most remarkably, we can even study ancient rocks on Earth to learn about the moon's tidal history. Certain sedimentary rocks preserve rhythmic patterns called tidal rhythmites, layered structures created by tidal cycles in ancient shallow seas. By counting these layers and analysing their patterns, geologists can determine how many days were in a month at the time those rocks were deposited, millions or hundreds of millions of years ago. This tells us how long the lunar orbital period was in the past, which in turn tells us how far away the moon was. The data from these ancient rocks confirms that the moon was closer to Earth in the past and that tidal effects were stronger then, exactly as predicted by the theory of tidal recession. All of these measurement techniques, from laser ranging to gravity mapping to geological studies to analysis of ancient rocks, combine to give us an extraordinarily detailed picture of how tidal forces work and how they have shaped the Earth-Moon system over billions of years. We are not speculating, we are measuring. We are testing predictions against observations, and every test confirms that our understanding is fundamentally correct. The moon is locked because tidal forces slowed its rotation until synchronous rotation was achieved. Those tidal forces continue to operate today, gradually pushing the moon farther away while slowing Earth's rotation. We can measure these effects happening in real time. We can see the evidence of them written in rock, billions of years old. The invisible becomes visible through careful observation, precise measurement, and mathematical analysis. The silent forces that shape worlds can be heard by those who know how to listen, who have the tools to detect them, who have the patience to collect data over decades and centuries. In our next section, we will explore what would happen if this delicate balance were disrupted, if somehow the moon's rotation changed, or if tidal forces suddenly ceased. Understanding stability requires understanding what would break it, what would disturb this perfect equilibrium that has endured for billions of years. The answer involves energy, momentum, and the stubborn persistence of physical law. Part 4. What would happen if the moon started spinning faster? Imagine for a moment that something disturbed the moon's perfect synchronous rotation. Perhaps a massive asteroid impact on the lunar far side, transferring enormous momentum. Perhaps some unknown force, some cosmic intervention that gave the moon a sudden push, accelerating its rotation. What would happen? Would the moon simply start spinning freely, breaking its tidal lock with Earth? Or would something else occur, some correction, some response from the universe itself? The answer reveals just how stable tidal locking really is, and why, once achieved, it persists so stubbornly across cosmic time. If the moon were somehow caused to rotate faster than its current locked rate, spinning more quickly than it orbits, the tidal bulges that are currently aligned with Earth would fall out of alignment. As the moon's surface rotated beneath those bulges, or rather as the bulges tried to maintain their alignment while the rest of the moon turned, tidal friction would immediately begin working again. The same process that originally slowed the moon's rotation would activate once more, creating internal heating, dissipating energy, and gradually reducing the spin rate back towards synchronous rotation. The timescale for this correction would depend on how much the rotation was disturbed. A small perturbation, perhaps increasing the rotation rate by just 1%, might be corrected within millions of years. A larger disturbance might take longer, but the direction would always be the same. The moon would always slow back down toward the locked state. This is because tidal locking represents a stable equilibrium, what physicists call an attractor in the system's dynamics. No matter how you disturb it, within reasonable limits, the system will naturally evolve back toward that equilibrium state. We can understand this mathematically using the concept of potential energy. In orbital mechanics, every configuration of a system has an associated energy level. Some configurations are higher in energy, less stable, more prone to change. Others are lower in energy, more stable, harder to disturb. Tidal locking represents a local minimum in the energy landscape of the Earth-Moon system. It is like a ball settled into the bottom of a bowl. If you push the ball up the side of the bowl, giving it extra energy, it will roll back down to the bottom once that energy dissipates through friction. The moon behaves the same way. NASA's orbital dynamics specialists have run detailed computer simulations of this scenario, testing what happens when they artificially increase the moon's rotation rate in their models. Every simulation shows the same result. The moon gradually slows back to synchronous rotation. The timescale varies depending on how much energy was added, but the outcome is always the same. The lock is stable, it persists. It resists disturbance. The amount of energy required to significantly disturb the moon's rotation is actually quite enormous. The moon is massive, with a total mass of about 7.3 times 10 to the power of 22 kilograms. Even though it rotates slowly, any change in that rotation rate involves changing the angular momentum of that entire mass. The kinetic energy of rotation, which depends on the moment of inertia and the square of the rotation rate, is substantial. To double the moon's rotation rate, you would need to add an amount of energy comparable to a large asteroid impact, something on the scale of the collision that created Tycho crater, one of the moon's youngest and most prominent impact features. Such impacts have occurred in the moon's history, of course. The lunar surface is covered with craters of all sizes, evidence of billions of years of bombardment by asteroids, comets, and meteoroids. Some of these impacts were surely large enough to give the moon a slight kick, adding or subtracting angular momentum, yet the moon remains locked. This tells us that even relatively large disturbances, impacts that created craters hundreds of kilometers across, were not sufficient to break the tidal lock permanently. The moon's rotation might have been temporarily disturbed, might have precessed or wobbled, but tidal forces would have worked to restore synchronous rotation over time. There is another interesting aspect to consider. What if the moon started spinning slower than its orbital period rather than faster? What if somehow it was rotating too slowly, completing less than one rotation per orbit? In this case, the tidal bulges would again fall out of alignment, but now in the opposite direction. Earth's gravity would work to speed up the moon's rotation rather than slow it down. The tidal torque would act in the direction to increase the spin rate, gradually bringing it back up to match the orbital period. Once again, synchronous rotation is the stable state toward which the system evolves. This reveals an important principle. Tidal locking is not just stable against disturbances in one direction, it is stable in both directions. Whether you spin the moon faster or slower, tidal forces will work to restore synchronous rotation. The equilibrium point is truly stable, what mathematicians call a globally stable equilibrium. This is part of why tidal locking is so common in the solar system. Once achieved, it is very difficult to break permanently. Temporary disturbances happen, but the system always returns to the locked state. Dr. Robin Canup, a planetary scientist who has studied tidal evolution extensively, explains it this way. Tidal locking is like a valley in a landscape. You can push a ball up the side of the valley, giving it potential energy, but when you let go, it rolls back down. The only way to get the ball out of the valley permanently is to give it enough energy to push it completely over the rim and into a different valley. For the moon, that would require such an enormous disturbance that it is essentially impossible through any known natural process. There is one scenario that could theoretically break tidal locking, though it is extraordinarily unlikely. If another large body, perhaps a rogue planet or a passing star, came close enough to the Earth-Moon system to gravitationally perturb it strongly, the Moon's orbit could be significantly altered. If the orbit changed dramatically enough, becoming much more elliptical or tilted, the simple relationship between orbital period and rotation rate might not hold anymore. The Moon might not settle back into synchronous rotation with its new orbit, but such an encounter is vanishingly improbable. The solar system is vast, mostly empty space, and close encounters between major bodies almost never happen. Another theoretical possibility is if the Moon captured a large satellite of its own, another smaller moon that began orbiting the Moon. The gravitational interactions between the Moon and its satellite could potentially affect the Moon's rotation, perhaps speeding it up or slowing it down through tidal forces. But this scenario is also highly unlikely. The Moon's gravity is relatively weak, and any object in orbit around the Moon would need to be in a very specific orbit to remain stable over long periods. Most likely, such an object would either crash into the Moon or escape from its weak gravitational grip. So when we consider all the possibilities, all the ways the Moon's rotation could be disturbed, we find that tidal locking is remarkably robust. It has persisted for billions of years. It will likely persist for billions more, until the Sun's evolution changes the fundamental conditions of the Earth-Moon system. The Moon will continue showing us the same face, the same patterns of dark Maria and bright highlands, the same familiar countenance that has watched over Earth since before life emerged from the oceans, since before the continents took their current shapes, since before our species looked up and wondered what that glowing disk in the night sky might be. There is something deeply satisfying about this stability, about knowing that some things in the universe persist, that not everything is in constant flux and change. The Moon's locked rotation, once achieved, became essentially permanent. It is a kind of cosmic memory, a record of gravitational interactions played out over time, frozen into the Moon's motion itself. In the next part of our exploration, we will look at the Moon's tidal effects on Earth, at how the relationship is not one-sided, at how the Moon's gravity shapes our world just as our gravity shaped the Moon. The invisible threads of gravity connect two worlds, and energy and momentum flow back and forth between them in an elegant exchange that has profound consequences for both. The dance continues, patient and precise, playing out across the void of space. Part 5. How does the Moon's gravity affect Earth's rotation? We have spent considerable time exploring how Earth's gravity affects the Moon, how it stretched and deformed our satellite, how it created tidal friction that slowed the Moon's rotation until synchronous locking was achieved. But gravity is reciprocal. Every force has an equal and opposite reaction, as Newton taught us in his third law of motion. If Earth's gravity pulls on the Moon, then the Moon's gravity must equally pull on Earth. And indeed it does, with profound consequences for our planet's rotation, its tides, and ultimately for life itself. The most obvious manifestation of the Moon's gravitational influence on Earth is the ocean tides. Twice each day, in most locations on Earth, the sea level rises to high tide and then falls back to low tide. This rhythm has been observed and recorded by coastal peoples for thousands of years, long before anyone understood what caused it. Ancient civilizations noticed the correlation between tides and the Moon's position in the sky, recognized that high tides occurred when the Moon was overhead or on the opposite side of the planet. But the mechanism remained mysterious until Newton provided the mathematical framework to understand it. The Moon's gravitational pull on Earth creates a tidal bulge in the oceans, very similar to the tidal bulge Earth creates on the Moon, but with an important difference. Earth's oceans are fluid, able to flow and deform much more easily than solid rock. When the Moon passes overhead, its gravity pulls the ocean water toward it, creating a bulge on the side of Earth facing the Moon. Simultaneously, on the opposite side of Earth, another bulge forms. This far side bulge exists because the moon's gravity pulls more strongly on Earth's centre than on the far side, effectively pulling Earth away from the water on that far side and leaving it bulged outward. As Earth rotates beneath these tidal bulges, carrying the continents and ocean basins through the pattern of high and low water, we experience the rise and fall of tides. At any given location, as you rotate into one of the bulges, the tide rises. As you rotate out of the bulge, the tide falls. Since there are two bulges, one on the near side and one on the far side, most locations experience two high tides and two low tides each day. The exact timing and magnitude of tides varies greatly depending on local geography, the shape of coastlines, the depth of the ocean, and other factors. But the fundamental cause is the moon's differential gravitational pull across Earth's diameter. But here is where it gets interesting, where the subtle but crucial physics comes into play. Earth is not a static body. It rotates, completing one turn every 24 hours. This rotation carries the tidal bulges along with it, but with a slight lag. Friction between the moving water and the ocean floor, friction within the water itself as it flows, and the complex dynamics of how water moves around continents and through ocean basins means that the tidal bulges do not stay perfectly aligned with the moon. They are dragged ahead slightly by Earth's rotation. Imagine looking down at Earth from above the North Pole. The moon is to the right, pulling on Earth's oceans and creating tidal bulges, but Earth is rotating counterclockwise. As it rotates, it tries to carry those tidal bulges around with it, pulling them ahead of the moon's position. The bulges never quite catch up to being directly under the moon. They stay a bit ahead, offset by perhaps a few degrees depending on location and ocean basin dynamics. This offset is crucial. This is where energy transfer occurs. Because the tidal bulges are offset ahead of the moon, rather than being aligned with it, they exert a gravitational pull on the moon that has a component in the direction of the moon's orbital motion. In other words, the bulges, being slightly ahead of where they should be, pull the moon forward in its orbit, giving it extra angular momentum. This speeds up the moon's orbital motion slightly, which, through the relationship between orbital velocity and orbital radius, causes the moon to move into a higher, more distant orbit. This is why the moon is gradually receding from Earth. But angular momentum must be conserved in the Earth-Moon system, assuming no external torques act on it. If the moon gains angular momentum by moving into a higher orbit, that momentum must come from somewhere. It comes from Earth's rotation. As the tidal bulges pull the moon forward, the moon's gravity simultaneously pulls back on those bulges, exerting a torque on Earth that opposes its rotation. This torque acts like a brake, gradually slowing Earth's spin. The result is a continuous transfer of angular momentum from Earth's rotation to the moon's orbit. Earth spins slower, days get longer, the moon orbits more slowly at a greater distance, months get longer. This process has been ongoing for billions of years and will continue for billions more. The rate of energy transfer, as we mentioned earlier, is approximately 3.7 terawatts, an enormous amount of power being continuously dissipated through tidal friction. We can measure this effect directly through several methods. Ancient coral fossils, which grow in layers similar to tree rings, show daily and yearly growth patterns. By counting these layers in corals hundreds of millions of years old, paleontologists have determined that there were more days in a year back then than there are now. The year has not changed in length. Earth's orbital period around the Sun is stable, but the day was shorter. There were about 400 days in a year during the Devonian period, roughly 400 million years ago, compared to 365 now. This implies that each day was only about 22 hours long back then. Similarly, ancient tidal rhythmites, sedimentary rocks that preserve the pattern of tides in ancient shallow seas, can be analysed to determine how many tides occurred per lunar month at the time those rocks were deposited. These analyses confirm that the moon orbited closer to Earth in the past, completing more orbits per year, and that tides were consequently stronger and more frequent. All the evidence points to the same conclusion. The moon was closer, Earth rotated faster, and tidal friction has been gradually slowing Earth while pushing the moon away. The rate of this slowdown is tiny on human timescales, but significant over geological time. Currently, Earth's day is lengthening by approximately 1.7 milliseconds per century. That might sound utterly negligible, and indeed it is imperceptible in daily life, but it accumulates over millions of years. Over 1 million years, Earth's day lengthens by about 17 seconds. Over 100 million years, it lengthens by about 28 minutes. Over the 4.5 billion year history of the Earth-Moon system, the day has lengthened from perhaps 6 hours in the immediate aftermath of the Moon's formation to the 24 hours we experience today. This slowing has profound implications for Earth's climate and environment. The length of day affects wind patterns, ocean currents, and weather systems. Early in Earth's history, when days were much shorter, winds would have been stronger and more turbulent. Weather patterns would have been more intense. The rapid rotation would have created stronger Coriolis effects, affecting how storms and currents developed. As the day has gradually lengthened, these effects have moderated, contributing to a more stable climate over time. The Moon's gravitational influence also helps stabilize Earth's axial tilt. Earth's rotation axis is tilted about 23.5 degrees relative to its orbital plane around the Sun. This tilt is responsible for our seasons. As Earth orbits the Sun, first one hemisphere tilts toward the Sun, receiving more direct sunlight and experiencing summer. Then 6 months later, that same hemisphere tilts away, receiving less direct sunlight and experiencing winter. Without this tilt, there would be no seasons, just an endless sameness as Earth circled the Sun. But axial tilt can change over time through complex gravitational interactions with other bodies in the solar system. The gravitational pulls of Jupiter, Saturn, and the other planets exert tiny but persistent torques on Earth. If Earth were alone, these torques could cause large variations in the tilt angle over millions of years, swinging from near 0 degrees to 30 or even 40 degrees. Such large variations would create dramatic climate instability, making it much more difficult for life to evolve and persist. The Moon prevents this. Its large mass and relatively close distance means its gravitational influence on Earth is substantial, far greater than any of the planets. This influence helps stabilize Earth's axial tilt, limiting the variations to just a degree or two over millions of years. Climate studies suggest that without the Moon, Earth's tilt could vary wildly, leading to periods where the poles receive more direct sunlight than the equator, or where the equator becomes ice-covered. Such variations would make Earth far less habitable. Dr. Jacques Lascar, an astronomer who has extensively modelled the long-term evolution of planetary orbits and spins, has shown through computer simulations that Earth without its Moon would likely experience chaotic variations in axial tilt. His models demonstrate that the Moon acts as a cosmic gyroscope, helping to hold Earth steady as it spins. This is one of the many ways that our large Moon contributes to Earth's habitability, making it a suitable home for complex life over billions of years. The tidal bulges in Earth's oceans are not the only tidal effects the Moon creates. The solid body of Earth also responds to the Moon's gravity, deforming slightly to create what are called earth tides or body tides. The entire planet, rock and all, bulges toward and away from the Moon by a few centimeters. This deformation is much smaller than ocean tides, which can rise and fall by meters, but it is measurable with sensitive instruments. As Earth's interior flexes in response to these tidal forces, friction occurs within the rock, generating heat. This tidal heating is tiny compared to Earth's internal heat from radioactive decay, but it exists, another channel through which energy is dissipated in the Earth-Moon system. All of these effects demonstrate that the Moon's influence on Earth is profound and multifaceted. The Moon is not merely a light in the night sky, a pretty object to gaze at during quiet evenings. It is an active participant in Earth's dynamics, affecting our rotation, our tides, our climate stability, even the length of our day. The gravitational threads connecting Earth and Moon are not abstract mathematical concepts. They are real forces, constantly pulling, constantly exchanging energy and momentum, shaping both worlds across deep time. In the next part of our journey, we will look at what we call libration, those small wobbles and oscillations that allow us to see slightly more than exactly half of the moon's surface. Even in the perfection of tidal locking, there exists subtle motion, gentle variations that reveal the moon's orbit is not quite as simple as it first appears. The mathematics becomes richer, the dance more intricate, when we look closely at the details. Part 6. Why can we see more than half of the moon's surface? If the moon were perfectly locked, showing us exactly the same hemisphere at all times with no variation whatsoever, we would see precisely 50% of its total surface from Earth, never any more, never any less. But patient observers have noticed something curious when they watch the moon carefully over weeks and months. The features at the very edge of the visible disk, the craters and mountains along what astronomers call the limb, shift slightly from one observation to the next. Sometimes we can see just a bit around the eastern edge, catching glimpses of features that were previously hidden. Other times we can peer around the western edge, or the northern or southern poles, seeing regions that were invisible before. Over time, if you map all the features visible from Earth across many lunar cycles, you discover that you can actually observe about 59% of the moon's total surface. Not simultaneously, of course. At any single moment, you still see only half. But the moon appears to wobble slightly, to nod and shake its head gently, revealing a bit more of its hidden face around the edges. This apparent wobbling motion is called libration, and it reveals that the moon's orbit and rotation, while locked on average, have subtle complexities that create small variations. There are three main types of libration, each arising from a different aspect of the moon's orbital geometry and motion. The first and most significant is called libration in longitude. This occurs because the moon's orbit around Earth is not a perfect circle. It is slightly elliptical, meaning the moon's distance from Earth varies as it travels along its orbital path. When the moon is at perigee, its closest approach to Earth, it is about 363,000 kilometers away. When it is at apogee, its farthest point, it reaches about 405,000 kilometers away. This difference of more than 40,000 kilometers may not sound like much compared to the average distance, but it is significant enough to affect orbital dynamics. Here is the key point. The moon's orbital speed changes as it moves closer to or farther from Earth. This is a consequence of Kepler's second law of planetary motion, which states that a line connecting a planet or moon to the body it orbits sweeps out equal areas in equal times. In practical terms, this means that when the moon is closer to Earth, at perigee, it moves faster in its orbit. When it is farther away, at apogee, it moves more slowly. The variation in orbital speed is approximately 300 meters per second between the fastest and slowest points. However, the moon's rotation rate remains constant. The moon spins on its axis at a perfectly steady rate, always taking exactly 27.3 days to complete one rotation. This rotation rate does not speed up or slow down as the moon moves through its elliptical orbit. So we have a situation where the moon's orbital speed varies while its rotation rate stays constant. This creates a mismatch. When the moon is moving faster in its orbit, its rotation cannot quite keep up, and we can see slightly around one edge. When the moon is moving slower in its orbit, its rotation gets slightly ahead, and we can see around the opposite edge. The result is that the moon appears to oscillate back and forth, swinging gently from side to side over the course of each orbit. This libration in longitude allows us to see about 8 degrees extra around each edge at different times, a substantial addition to the visible surface. Ancient astronomers noticed this effect and gave it the name libration from the Latin word for balance or scales, because the motion resembles the gentle swaying of a balance scale. The second type of libration is called libration in latitude. This occurs because the moon's rotation axis is not perfectly perpendicular to its orbital plane. Instead, it is tilted by about 6.5 degrees. As the moon orbits Earth, this tilt means that sometimes we're looking slightly down on the moon's north pole, seeing features near the northern limb that would otherwise be hidden. Half an orbit later, we are looking slightly up from below, seeing features near the southern limb instead. This oscillation allows us to peer about 7 degrees around the north and south poles at different times throughout the month. The physical cause of this axial tilt is related to the moon's formation and early tidal evolution. When the moon first formed, its rotation axis could have been oriented at any angle. As tidal locking proceeded, the axis gradually settled into a configuration that minimized energy, but that configuration retained a small tilt relative to the orbital plane. This tilt has persisted for billions of years, a frozen memory of the moon's complex dynamical history. The third type of libration is called diurnal libration, and it is the smallest of the three effects, but perhaps the most interesting conceptually. It arises from a change in viewing perspective as Earth rotates. When you observe the moon rising above the eastern horizon in the evening, you are viewing it from one edge of Earth's diameter. 12 hours later, when the moon is setting in the west, you are viewing it from the opposite edge of Earth's diameter, a distance of more than 12,000 kilometers away from your first viewing position. This change in viewpoint allows you to see about 1 degree around opposite edges of the moon at different times of night. Diurnal libration is small compared to the longitudinal and latitudinal librations, but it reminds us that our perspective on the moon is affected not only by the moon's motion, but also by our own motion as observers rotating with Earth. Every observation of the moon is made from a planet that is spinning, orbiting, tilted, and moving through space. When we account for all these motions, the apparent simplicity of the moon's steady face becomes a much more complex and dynamic picture. When you combine all three types of libration together, accounting for the elliptical orbit, the tilted axis, and the changing viewpoint from Earth's rotation, you get the total libration amplitude that allows us to see 59% of the moon's surface over time. The remaining 41%, the true far side that remains forever hidden from Earth, was completely unknown to humanity until the Soviet Luna 3 spacecraft photographed it in 1959, giving us our first glimpse of that mysterious hidden hemisphere. The far side of the moon, it turned out, is quite different from the near side. It has far fewer of the dark volcanic plains called Maria, which give the near side its distinctive appearance of a face with eyes and mouth. Instead, the far side is heavily cratered, rougher, more ancient in appearance. Scientists believe this difference may be related to the tidal locking itself. Early in the moon's history, when it was still partially molten, tidal heating from Earth was concentrated on the near side, the hemisphere facing us. This additional heating may have made it easier for volcanic lava to reach the surface on the near side, flooding low-lying impact basins and creating the Maria we see today. The far side, receiving less tidal heating, remained more geologically static, preserving its ancient cratered surface. Libration also affects the illumination of the moon's polar regions. Near the lunar poles, there are deep craters whose floors are never illuminated by sunlight because of the moon's very small axial tilt. These permanently shadowed regions are some of the coldest places in the solar system, with temperatures dropping below -200 degrees Celsius. Scientists believe water ice may be trapped in these shadows, deposited by comet impacts over billions of years and preserved in the eternal cold. Future lunar missions plan to explore these regions, searching for water resources that could support human exploration and eventual settlement. The mathematical description of libration involves combining the equations for the moon's elliptical orbit with the equations describing its rotation. The result is a set of periodic oscillations with different amplitudes and frequencies. The dominant oscillation, libration in longitude, has the same period as the moon's orbital period, approximately 27.3 days. Libration in latitude also has this same period, but is 90 degrees out of phase, reaching its maximum when longitudinal libration is at 0. Diurnal libration has a period of 1 day, the rotation period of Earth. NASA has created detailed models of lunar libration that can predict exactly how much of the moon's surface is visible from any location on Earth at any given time. These models are important for planning observations with telescopes, for timing spacecraft communications when certain lunar features need to be visible from Earth, and for understanding the long-term stability of the Moon's orientation. The models confirm that libration is completely understood and perfectly predictable, a natural consequence of orbital mechanics with no mysteries remaining. Some observers have suggested that libration proves the Moon is not truly locked, that it is still rotating independently of its orbit. This is a misunderstanding. The Moon is indeed tidally locked. Its average rotation rate exactly matches its average orbital period. The librations are small oscillations around this average, temporary deviations caused by the non-circular orbit and tilted axis, not evidence of independent rotation. It is like a pendulum that hangs straight down on average but swings slightly from side to side. The average position is still straight down. The pendulum has not broken free. Similarly, the Moon's average orientation is locked, even though small oscillations occur around that locked state. Interestingly, as the Moon continues to recede from Earth over millions of years, the amplitude of libration will gradually change. As the orbit becomes larger, the gravitational interactions that create libration will slightly weaken, reducing the oscillations. But this is an incredibly slow process, essentially imperceptible over human timescales. For all practical purposes, libration will continue at its current amplitude for millions of years into the future. For amateur astronomers, libration creates interesting observing opportunities. If you want to see a particular feature near the Moon's limb, you need to wait for the right phase of libration when that feature is tilted toward Earth. Specialized astronomy software can calculate these times, allowing you to plan your observations. Professional astronomers studying the lunar surface also take libration into account, imaging the same regions during different libration states to build up three-dimensional maps of the terrain near the edges. In summary, libration is a beautiful demonstration that even the most stable astronomical phenomena have subtle complexities when examined closely. The Moon's tidal locking is perfect on average, a remarkable equilibrium achieved over billions of years. But zoom in, look at the fine details, and you find gentle oscillations, small wobbles, periodic variations that reveal the richness of orbital dynamics. The universe rewards careful observation. Nothing is quite as simple as it first appears. And in that complexity, in those subtle details, we find deeper understanding and greater appreciation for the elegant mathematics that governs celestial motion. Part 7. How does tidal locking affect other moons in the solar system? Earth's moon is not alone in experiencing tidal locking. This phenomenon is remarkably common throughout the solar system, particularly among the many moons orbiting the giant planets Jupiter, Saturn, Uranus, and Neptune. Each of these gas giants possesses dozens of satellites, and nearly all of the larger ones are tidally locked to their parent planet, always showing the same face inward. This universality tells us something profound about the nature of gravity and orbital mechanics. Tidal locking is not a special condition. It is the natural end state for most satellite systems, the stable configuration toward which gravity relentlessly drives them. Consider Jupiter, the largest planet in our solar system, with a mass more than 300 times that of Earth. Jupiter has at least 95 known moons, though many are tiny captured asteroids barely a few kilometers across. The four largest Galilean moons, discovered by Galileo Galilei in 1610, when he first pointed the telescope at Jupiter, are Io, Europa, Ganymede, and Callisto. All four are tidally locked, each presenting the same hemisphere toward Jupiter throughout their orbits. Io, the innermost of the Galilean moons, is perhaps the most dramatic example of tidal effects in action. It orbits Jupiter at a distance of only 422,000 kilometers, less than the distance from Earth to our moon. But Jupiter's mass is so enormous, its gravitational pull so intense, that the tidal forces acting on Io are extraordinarily strong. As Io orbits, Jupiter's gravity stretches and squeezes it constantly, flexing the moon's interior. This flexing generates tremendous amounts of heat through friction, far more than could be produced by radioactive decay alone. The result is that Io is the most volcanically active body in the solar system. it has hundreds of active volcanoes erupting continuously, spewing sulfur and sulfur dioxide high into space, coating the surface with colourful deposits of yellow, orange, red and white. The volcanic plumes can reach heights of several hundred kilometres. The heat generated by tidal friction is so intense that it melts rock deep inside Io, creating vast chambers of magma that feed the surface volcanoes. NASA's Voyager spacecraft, which flew past Jupiter in 1979, captured images of volcanic eruptions in progress, confirming that Io's volcanism is active and ongoing, powered entirely by tidal heating. The situation with Io is actually more complex than simple tidal locking. Io is locked in an orbital resonance with Europa and Ganymede, the next two Galilean moons outward. For every one orbit Io completes around Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 4 orbits. This precise mathematical relationship, called a Laplace resonance, means that the 3 moons periodically align with each other, creating additional gravitational perturbations that prevent Io's orbit from becoming perfectly circular. The orbit remains slightly elliptical, and this eccentricity ensures that tidal forces continue to vary as Io orbits, maintaining the intense tidal heating. Europa, the second Galilean moon, is also tidally locked and also experiences significant tidal heating, though not as extreme as Io. Europa's surface is covered by a shell of water ice, but beneath that ice, scientists believe there exists a liquid water ocean, kept from freezing by tidal heat. The evidence for this ocean comes from multiple sources, including measurements of Europa's gravitational and magnetic fields made by the Galileo spacecraft, which orbited Jupiter from 1995 to 2003. The ocean may be tens of kilometers deep, containing more water than all of Earth's oceans combined. This subsurface ocean makes Europa one of the most promising places in the solar system to search for extraterrestrial life. Liquid water, chemical nutrients dissolved from the rocky mantle below, and energy from tidal heating create conditions that could potentially support microbial life similar to organisms that live near hydrothermal vents on Earth's ocean floor. Future missions, including NASA's Europa Clipper, will study this moon in detail, searching for evidence of the ocean and any potential biosignatures. Ganymede, the largest moon in the solar system, even bigger than the planet Mercury, is also tidally locked to Jupiter. It too likely has a subsurface ocean maintained by a combination of tidal heating and residual heat from its formation. Ganymede is unique among moons in having its own magnetic field, generated by a liquid iron core that continues to convect and create a magnetic dynamo. The interaction between Ganymede's magnetic field and Jupiter's powerful magnetosphere creates complex patterns of charged particles and auroras near Ganymede's poles. Callisto, the outermost Galilean moon, orbits at a greater distance and experiences weaker tidal forces. It is also tidally locked, but does not show the intense geological activity of the inner moons. Its surface is heavily cratered, ancient, geologically dead. It represents what might have happened to Europa or Ganymede if tidal heating had not kept their interiors active over billions of years. Moving to Saturn, we find another family of tidally locked moons. Titan, Saturn's largest satellite and the second largest moon in the solar system, is tidally locked and orbits Saturn every 16 days. Titan is extraordinary in many ways. It is the only moon with a thick atmosphere, denser at the surface than Earth's atmosphere. This atmosphere is mostly nitrogen, with traces of methane and other hydrocarbons. Methane on Titan plays a role similar to water on Earth, existing as liquid, gas and solid depending on temperature. Titan has methane rain, methane rivers and methane lakes and seas near its poles. The Cassini-Huygens mission, which studied Saturn and its moons from 2004 to 2017, revealed Titan to be a complex world with weather, erosion, and an active hydrological cycle, all based on methane instead of water. The Huygens probe, which descended through Titan's atmosphere and landed on the surface in January 2005, sent back images showing a landscape shaped by liquid flow, with rounded cobbles and drainage channels, all carved by methane rather than water. Titan's tidal locking is complicated by its thick atmosphere and possible subsurface ocean. The atmosphere can exchange angular momentum with the surface, creating winds that accelerate or decelerate the rotation slightly. Meanwhile, a subsurface water ocean, if it exists, would be decoupled from the solid surface, allowing the ice shell to rotate at a slightly different rate than the deep interior. Measurements from Cassini suggest these effects are real but small, not enough to break the overall tidal lock with Saturn. Enceladus, another of Saturn's moons, much smaller than Titan, is also tidally locked and is another target for astrobiology. Despite being only about 500 kilometers in diameter, barely larger than a modest asteroid, Enceladus shows dramatic geological activity. The Cassini spacecraft discovered enormous plumes of water vapor erupting from cracks near Enceladus's south pole, shooting water and ice particles hundreds of kilometers into space. These plumes are fed by a subsurface ocean beneath the ice shell, warmed by tidal heating from Saturn's gravity. The water vapor in the plumes has been analyzed and found to contain organic molecules, salts, and other chemicals consistent with hydrothermal activity on the ocean floor. This makes Enceladus another prime candidate for harboring microbial life, despite its small size and great distance from the Sun. The tidal heating that powers this activity is possible because Enceladus, like Io, is locked in an orbital resonance with other moons, maintaining a slightly elliptical orbit that creates varying tidal stress. Beyond Saturn, the ice giant planets Uranus and Neptune also have tidally locked moons. Miranda, one of Uranus's major satellites, is tidally locked and has a bizarrely complex surface, with sharp boundaries between different terrain types, suggesting a violent geological history. Triton, Neptune's largest moon, is also tidally locked, but is unusual in orbiting retrograde, moving opposite to Neptune's rotation. This suggests Triton was captured from the Kuiper belt, rather than forming in place around Neptune. Despite being far from the Sun and receiving very little solar energy, Triton shows evidence of recent geological activity, including nitrogen geysers erupting from its surface, likely powered by a combination of tidal heating and solar warming of subsurface nitrogen ice. Even dwarf planets can experience tidal locking. Pluto and its largest moon Charon are mutually tidally locked, meaning each body always shows the same face to the other. Pluto rotates once every 6.4 days, and Charon orbits Pluto at exactly the same period. If you stood on the surface of Pluto facing Charon, that moon would hover motionless in your sky, never rising or setting. Similarly, from Charon's surface, Pluto would be fixed in the sky. This mutual locking is relatively rare in the solar system because it requires both bodies to be similar enough in mass that tidal forces can affect both significantly. The prevalence of tidal locking throughout the solar system confirms that it is a natural, inevitable outcome of gravitational interactions over time. Any moon orbiting close enough to its parent planet where tidal forces are strong will eventually become locked. The timescale depends on the masses involved, the distance, and the internal structure of the moon, but the end result is always the same if enough time passes. Gravity is patient. It works slowly but inexorably, dissipating energy, exchanging momentum, driving systems toward equilibrium. What about moons that are not tidally locked? They do exist, but are much rarer among large satellites. They tend to be small captured asteroids in distant, highly elliptical orbits where tidal forces are too weak to have caused locking during the age of the solar system. Mars's two tiny moons, Phobos and Deimos, are tidally locked despite their small size because they orbit very close to Mars. But many of the outer irregular satellites of Jupiter, Saturn, and the other giants, captured objects in distant retrograde orbits, have not locked and rotate independently. The study of tidal locking in the solar system has implications beyond just understanding our cosmic neighborhood. As astronomers discover exoplanets around other stars, many of which are close enough to their parent stars to experience strong tidal forces, the question of tidal locking becomes important for understanding those distant worlds. A planet tidally locked to its star, sometimes called an eyeball planet, would have one hemisphere in permanent daylight and the other in permanent night, creating extreme temperature differences and unusual climate patterns. Yet such planets might still be habitable in a twilight zone near the terminator, the boundary between day and night, where temperatures remain moderate. The mathematics that explains tidal locking in our solar system applies equally to these exoplanetary systems. The same equations, the same principles, the same gradual dissipation of energy through friction all operate universally. Gravity knows no boundaries. Physics applies everywhere. The locked moons of Jupiter teach us about the locked planets of distant stars. The dynamics of the Earth-Moon system illuminate the dynamics of countless other satellite and planetary systems across the galaxy. In the next part of our exploration, we will look at the specific mathematics that governs tidal locking, the equations that allow scientists to predict when and how it occurs, and the physical principles underlying those equations. The language of mathematics, precise and universal, gives us the tools to understand and predict these cosmic phenomena with extraordinary accuracy. Numbers can be poetry when they describe the motion of worlds. Part 8. What mathematics describes tidal locking? To truly understand tidal locking, to grasp it not just as a qualitative phenomenon, but as a precise, quantitative reality, we must venture into mathematics. This might seem daunting, but the core concepts are actually quite elegant once you understand the basic principles. And unlike human languages, which can be ambiguous and culturally dependent, mathematics is universal. The equations describing tidal locking work the same way here on Earth as they do in the most distant galaxy. They are eternal truths woven into the structure of the universe itself. Let us begin with the most fundamental equation, Newton's law of universal gravitation, which we have already encountered. The gravitational force between two masses, let us call them Earth and Moon, depends on the product of their masses and inversely on the square of the distance between their centers. Written symbolically, force equals the gravitational constant times mass 1 times mass 2 divided by distance squared. This elegant relationship was one of Newton's greatest achievements, unifying the motion of falling apples with the motion of orbiting moons. But for tidal locking, we need to go beyond this basic gravitational force and consider tidal forces, which arise from the gradient of gravity across a body. The key insight is that gravity is not uniform. The side of the Moon facing Earth experiences stronger gravitational attraction than the far side because it is closer to Earth. This difference in gravitational force across the Moon's diameter is what creates the tidal bulge, and it is this difference that we need to quantify mathematically. The tidal force can be approximated using calculus by taking the derivative of the gravitational force with respect to distance and then multiplying by the radius of the Moon. Without diving into complex notation, the result is that the tidal force is proportional to the mass of Earth, the radius of the Moon, and inversely proportional to the cube of the distance between Earth and Moon's centers. Note the cube, not the square. This means tidal forces fall off much more rapidly with distance than gravitational forces do. Double the distance and tidal forces drop to 1/8 of their previous value. This is why moons far from their planets experience much weaker tidal effects. The next piece of mathematics we need involves torque, the rotational equivalent of force. Torque determines how quickly something changes its rotation rate. For the Moon, the torque arises from the gravitational pull that Earth exerts on the Moon's tidal bulge. If the bulge is perfectly aligned with the Earth-Moon line, the torque is zero because the forces are symmetric. But if the bulge is offset, as it would be if the Moon is rotating faster or slower than the synchronous rate, then there is a net torque that acts to change the Moon's rotation. The magnitude of this tidal torque depends on several factors. It depends on the masses of the two bodies involved. It depends on the distance between them, with the torque falling off extremely rapidly with distance, proportional to the 6th power of the distance. It depends on the size of the tidal bulge, which itself depends on how deformable the Moon is. And it depends on something called the tidal dissipation factor, often denoted by the letter Q, which measures how efficiently energy is dissipated inside the Moon as it flexes. Materials with low Q values dissipate energy efficiently, meaning they heat up significantly when flexed and thereby create strong tidal torques. Materials with high Q values are more elastic, storing and releasing energy without much dissipation, creating weaker torques. Earth's moon has a relatively high Q value because its interior is largely solid rock, which is fairly elastic compared to, say, a liquid interior. In contrast, Io has a much lower Q value because its interior is partially molten, making it easier to deform and heat. The rate at which the moon's rotation changes can be written as an equation involving all these factors. The change in angular velocity per unit time equals a constant that depends on material properties multiplied by terms involving the masses, the distance, the radius, and the dissipation factor. When scientists input the known values for the Earth-Moon system into this equation, they can calculate how long it would take for tidal locking to occur starting from various initial conditions. The results show that if the moon started out rotating once every few hours, as it likely did shortly after its formation, and if Earth's gravity has been acting on it for 4.5 billion years, then tidal locking should definitely have occurred by now. In fact, the calculations suggest the moon probably locked within the first few 100 million years of its existence, perhaps even faster. The exact timescale is uncertain because we don't know precisely what the moon's initial rotation rate was, or exactly what its Q value was when it was younger and hotter. There is another important equation in this story, one that describes the conservation of angular momentum in the Earth-Moon system. Angular momentum, roughly speaking, measures the amount of rotation in a system. For a spinning object, angular momentum depends on its mass, its size, and how fast it is spinning. For an orbiting object, it depends on the mass, the orbital distance, and the orbital velocity. The crucial principle is that unless external torques act on the system, the total angular momentum remains constant. In the Earth-Moon system, the total angular momentum is the sum of Earth's rotational angular momentum, the Moon's rotational angular momentum, and the Moon's orbital angular momentum. As tidal friction causes Earth to spin slower, it loses rotational angular momentum. But that momentum does not disappear. It gets transferred to the Moon's orbit, increasing the orbital angular momentum. This causes the Moon to spiral outward to a larger orbit. Similarly, when the Moon's rotation was slowing due to tidal forces, its rotational angular momentum decreased, but that momentum was transferred elsewhere in the system. By setting up equations that describe how angular momentum flows between Earth's spin, the Moon's spin, and the Moon's orbit, scientists can model the entire tidal evolution history of the system. They can run these equations backward in time to see where the Moon was billions of years ago, confirming that it was much closer to Earth when it first formed. They can run them forward in time to predict where the Moon will be in the future, showing that it will continue drifting away until mutual tidal locking is achieved billions of years from now. The mathematics also allows us to understand why tidal locking happens in the first place from an energy perspective. Every physical system naturally evolves toward its lowest energy state if given enough time and a mechanism for dissipating energy. For the Earth-Moon system, the lowest energy state that conserves angular momentum is synchronous rotation. Any other configuration has higher energy, which can be dissipated through tidal friction until the lowest state is reached. Think of it like a ball rolling down a hill in the presence of friction. The ball has potential energy at the top of the hill. As it rolls down, that potential energy converts to kinetic energy, the energy of motion. But friction with the ground causes some of that energy to dissipate as heat. Eventually, the ball reaches the bottom of the hill and stops, sitting at the lowest potential energy point. It cannot spontaneously roll back up the hill because that would require adding energy back into the system. Similarly, once the Moon reaches tidal lock, it cannot spontaneously unlock without external input of energy or angular momentum. The precise equations governing all of this were worked out over many decades by scientists studying celestial mechanics. Pioneer work was done by George Howard Darwin, son of Charles Darwin, in the late 19th century. He developed the mathematical framework for understanding tidal evolution and was the first to suggest that the moon might have originated from Earth through fission. While that particular formation theory turned out to be incorrect, his mathematical methods for studying tidal interactions remain valuable and are still used today with modern refinements. In the 20th century, scientists like Peter Goldreich and Stan Peele further developed the theory, incorporating better understanding of planetary interiors and material properties. They showed how different assumptions about Q values and other parameters affect the timescale for tidal locking, and made predictions that could be tested against observations of other moons in the solar system. Their work laid the foundation for our current understanding. Modern computer simulations can now solve these equations numerically with great precision, tracking the evolution of orbital systems over billions of years of simulated time. Scientists input initial conditions, such as the moon's starting distance and rotation rate, along with the physical parameters like masses and Q values. The computer then steps forward through time, calculating at each step how the tidal forces affect the rotation rates and orbital distance. These simulations can reproduce the current Earth-Moon system accurately, giving confidence that the underlying mathematics is correct. One particularly elegant aspect of the mathematics is how it connects tidal locking to energy dissipation. The rate at which energy is dissipated through tidal friction equals the tidal torque multiplied by the angular velocity difference between synchronous rotation and actual rotation. When the moon is locked, this difference is zero, so no energy is being dissipated in the moon's rotation, but energy is still being dissipated in Earth's tides, causing the moon to gradually recede. Only when both bodies are mutually locked will all tidal dissipation cease. The equations also explain the obliquity damping, the process by which tidal forces cause a moon's axial tilt to gradually decrease over time. If a moon starts with a large tilt, the varying tidal forces as the moon orbits create additional friction that dissipates the rotational energy associated with that tilt. Over time, the axis straightens out, minimizing this source of dissipation. Our moon's small axial tilt of about 6.5 degrees is probably a residual from this process, not quite damped to zero, but significantly reduced from whatever it might have been initially. Mathematically describing these phenomena requires differential equations, tools from calculus that describe how quantities change over time. The change in the moon's spin rate depends on the current spin rate, the orbital parameters, and the physical properties. The change in orbital distance depends on how much energy is being dissipated and transferred. These equations are coupled, meaning you cannot solve one without considering the others. But modern mathematical and computational techniques handle such coupled systems routinely. For students and researchers learning about tidal locking, working through these equations provides deep insight into the physics. You begin to see how everything connects, how a small difference in distance creates a force gradient, how that gradient creates torque, how torque changes rotation, how that change affects energy dissipation, how energy dissipation requires angular momentum transfer, and how that transfer changes the orbit. It is a beautiful web of cause and effect, all governed by precise mathematical relationships. The universality of mathematics means these same equations apply to any tidally evolving system anywhere in the universe. Whether we are studying the Earth-Moon pair, the Jupiter-Io system, or an exoplanet locked to its star, the fundamental mathematics is identical. Only the input parameters change. This is part of what makes physics so powerful. We can understand phenomena across vast scales and distances using the same core principles and equations. In essence, the mathematics of tidal locking is an expression of how nature operates, how gravity and friction conspire over cosmic time to create order out of chaos, to drive systems toward equilibrium, to lock satellites into synchronous dances with their parent worlds. The equations are not just descriptions, they are predictions. They tell us what must happen given sufficient time, and observations confirm those predictions again and again. Mathematics and reality align, revealing truths about the cosmos that transcend human cultures, languages, and civilizations. Part 9. What role does the moon's tidal locking play in Earth's history? The moon's tidal locking is not merely an astronomical curiosity, something interesting for scientists to study, but ultimately irrelevant to daily life. On the contrary, the gravitational relationship between Earth and Moon, the tidal forces they exert on each other, and the gradual evolution of their orbital dance have played crucial roles in shaping Earth's history, its geology, its climate, and even the evolution of life itself. To understand Earth, you must understand the Moon. To understand life, you must understand the tides. Let us begin with the most obvious influence, the ocean tides that rise and fall twice each day in response to the Moon's gravitational pull. These tides are not just gentle variations in sea level. They represent enormous movements of water, hundreds of billions of tons shifting across the planet's surface every few hours. In some locations, particularly in narrow bays and inlets with the right geometry, tidal ranges can exceed 10 meters, creating dramatic differences between high and low tide. The Bay of Fundy, located between New Brunswick and Nova Scotia in eastern Canada, experiences the highest tides in the world, with a maximum range approaching 17 meters during spring tides, when the sun and moon align to create especially strong tidal forces. Watching the tide come in at the Bay of Fundy is like watching a slow-motion tsunami, an inexorable wall of water advancing up the bay, filling mudflats and channels that were dry just hours before. These powerful tides affect coastal ecosystems profoundly. Intertidal zones, the regions between high and low tide marks, create unique habitats that are sometimes submerged and sometimes exposed to air. Organisms living in these zones must adapt to extreme conditions, surviving both underwater environments and terrestrial exposure, handling temperature fluctuations, salinity changes, and predation from both marine and land animals. The tides have shaped the evolution of countless species, from barnacles and mussels to crabs and shorebirds. Early in Earth's history, when the moon was much closer and tides were correspondingly stronger, these effects would have been even more dramatic. Some scientists have suggested that tidal pools, those small bodies of water trapped in depressions at low tide, may have played a role in the origin of life. These pools would undergo regular cycles of dilution and concentration as tides came and went, potentially helping to concentrate organic molecules and drive chemical reactions that led to the first self-replicating molecules. While this remains speculative, it illustrates how the moon's tidal effects could have influenced even the most fundamental transitions in Earth's history. The tides also drive significant energy dissipation, as we have discussed. The movement of water against coastlines, the friction within ocean basins as tidal currents flow, the flexing of the solid earth beneath the oceans, all of this dissipates approximately 3.7 terawatts of power continuously. This energy ultimately comes from the rotational and orbital energy of the Earth-Moon system, causing Earth's rotation to slow and the Moon to recede. Over geological time, this has had measurable effects on the length of day and the distance to the Moon. During the Precambrian era, roughly 1 billion years ago, Earth's day was only about 18 hours long. The faster rotation would have created stronger Coriolis effects, affecting wind patterns and ocean currents. Weather systems would have been more intense, hurricanes stronger, climate potentially more variable. As the day gradually lengthened to its current 24 hours, these effects moderated. Some climate scientists believe this gradual slowing of Earth's rotation contributed to climate stability, making the planet more hospitable for complex life. The Moon also stabilizes Earth's axial tilt, a crucial factor for long-term climate stability. Earth's axis is tilted approximately 23.5 degrees relative to its orbital plane around the Sun. This tilt creates our seasons, as different hemispheres tilt toward or away from the Sun during the year. But this tilt is not fixed on very long timescales. Gravitational interactions with Jupiter, Saturn, and the other planets create tiny torques that could, over millions of years, cause significant changes in Earth's obliquity, the technical term for axial tilt. Computer simulations of Earth without a moon show that obliquity could vary chaotically between 0 and 85 degrees over tens of millions of years. Such variations would create wild climate swings. Imagine if Earth's poles sometimes pointed nearly at the Sun. The Arctic and Antarctic would experience direct sunlight for months at a time, becoming far warmer than the tropics, then millions of years later, the equator might be tilted to receive the most direct sunlight, with poles in constant frigid darkness. Such variations would make it extremely difficult for complex ecosystems to persist, as climate zones would shift dramatically over timescales too short for species to adapt through evolution. The Moon prevents this chaos. Its large mass and relatively close orbit create a strong gravitational torque on Earth's equatorial bulge, the slight widening of Earth at the equator caused by its rotation. This torque acts like a gyroscope stabilizing mechanism, keeping the tilt angle relatively constant. Variations still occur, oscillating between about 22 and 24.5 degrees over a cycle of about 41,000 years, but these are small compared to the wild swings that would happen without the Moon. This stability has allowed Earth's climate zones to remain in roughly the same latitudes for hundreds of millions of years, giving life time to adapt and diversify. Tropical ecosystems have remained near the equator, allowing rainforests to develop complex interdependencies. Polar ice caps have remained at the poles, driving ocean circulation through the sinking of cold, dense water. Temperate zones have stayed in the mid-latitudes, supporting the grasslands and forests that many species depend on. Remove the Moon, and all of this stability vanishes. The Moon's influence extends to Earth's geology as well. The tidal flexing of the solid Earth, though small, generates heat through friction. This tidal heating is minor compared to the heat generated by radioactive decay in Earth's interior, but it exists and contributes to keeping Earth's interior slightly warmer than it otherwise would be. Some geophysicists have speculated that this extra heat may have prolonged Earth's plate tectonic activity, helping to maintain a hot, convecting mantle that drives continental drift and volcanic activity. Plate tectonics is crucial for life because it recycles carbon between the atmosphere, oceans, and rocks. Carbon dioxide is removed from the atmosphere through weathering of rocks and burial of organic material. It is returned through volcanic outgassing. This carbon cycle regulates Earth's greenhouse effect, keeping temperatures in a range suitable for liquid water, despite changes in solar luminosity over geological time. Without plate tectonics, this regulatory cycle might not function, and Earth could experience runaway greenhouse heating or snowball glaciation. The Moon's contribution to maintaining plate tectonics, if real, would be another way it has supported life. There is also a more speculative idea that the Moon's presence may have influenced the evolution of intelligence on Earth. The argument goes like this. Tides create complex, ever-changing coastal environments with strong selective pressures. Early animals that could predict tides, remember tide timing, navigate based on lunar cycles, would have advantages. These cognitive demands may have driven the evolution of more complex nervous systems and eventually brains. While highly speculative and difficult to test, it is an intriguing possibility that our capacity for abstract thought might be indirectly connected to the Moon's tidal influence. The Moon has also been practically important to human civilization. Before artificial lighting, the Moon provided significant illumination at night, especially during full moon, when its brightness approaches -13 magnitude, bright enough to read by if your eyes are well adapted. Ancient peoples scheduled activities around lunar phases, traveling and working outdoors during full moons when visibility was best. Many cultures developed lunar calendars, tracking months based on the time between successive full moons, approximately 29.5 days. The regularity of lunar phases also provided one of humanity's first lessons in celestial mechanics in the predictability of nature. Ancient astronomers, observing carefully and keeping records over generations, learned to predict lunar eclipses, to calculate the Moon's position months or years in advance. This demonstrated that the heavens followed laws, that nature was not entirely capricious, that through observation and thought, humans could understand and predict cosmic events. This realization was foundational for the development of science. In more recent times, the Moon has inspired space exploration, serving as humanity's first destination beyond Earth. The Apollo program, which landed 12 astronauts on the lunar surface between 1969 and 1972, represented one of the greatest technological achievements in human history. The samples returned from the moon, totaling about 382 kilograms of lunar rock and soil, have been invaluable for understanding the moon's composition, age, and formation history. Those samples confirmed that the moon is about 4.5 billion years old, roughly the same age as Earth, supporting the giant impact hypothesis for lunar formation. Future lunar exploration may reveal resources that could support deeper space exploration. Water ice in permanently shadowed polar craters could provide drinking water, oxygen for breathing, and hydrogen for rocket fuel. Lunar regolith, the layer of loose rock and dust covering the surface, contains oxygen bound in minerals that could potentially be extracted. Helium-3, a rare isotope on Earth but more abundant in lunar soil, has been proposed as a possible fuel for future fusion reactors. While these resources remain speculative for now, they illustrate how the moon might continue to play a role in human activity beyond its gravitational influence. The cultural impact of the moon is immeasurable. It appears in the mythology, art, literature, and music of every human culture. The moon has been worshipped as a deity, feared as a bringer of madness, celebrated as a symbol of beauty and romance, studied as a subject of scientific inquiry. The word lunacy derives from the Latin word for moon, luna, reflecting ancient beliefs that the moon influenced mental health. While modern science finds no evidence for such effects, the cultural legacy persists. In summary, the moon's tidal locking and gravitational influence have shaped Earth in profound ways over billions of years. The tides have created unique ecosystems, possibly influenced the origin of life, and driven the gradual slowing of Earth's rotation. The stabilization of Earth's axial tilt has maintained climate zones that allowed complex life to flourish. The presence of a large nearby satellite has affected Earth's geology, provided illumination for pre-industrial societies, inspired scientific and philosophical thought, and served as the first destination for human space exploration. To understand Earth's history, you cannot ignore the moon. The two bodies are intimately connected, partners in a gravitational dance that has profoundly shaped both worlds. Part 10. Will the moon ever escape or stop facing Earth? One day, far in the future, almost unimaginably distant from our present moment, a single day on Earth will last as long as what we now call a month. The oceans will no longer rise and fall in their ancient rhythm. The tides that have breathed with the planet for billions of years will finally rest, becoming still. And in the silent sky above, the moon will hover motionless, frozen in place above one hemisphere of our world, eternally fixed in its position, like a painted disc on the dome of heaven. That is not science fiction born from wild imagination. It is the mathematically inevitable final stage of a slow, ongoing process that began the very moment the moon was born from cosmic violence. Right now, at this present moment, the moon is drifting away from Earth at approximately 3.8 centimeters per year. This tiny rate of recession, barely the width of 2 fingers placed side by side, has been confirmed with extraordinary precision by NASA's Lunar Laser Ranging experiments. These experiments have been tracking the reflection of laser light from retroreflectors placed on the moon's surface by Apollo astronauts continuously for more than 50 years, building a database of measurements that shows unmistakably that the moon is gradually, inexorably moving farther from us. This gradual retreat is powered by tidal friction, the same invisible mechanism that once locked the moon's rotation to its orbit around Earth. But the process has not ended with that locking. Energy continues to be exchanged between Earth's spin and the moon's orbit, quietly and relentlessly, through every tide that rolls across our planet's surface, through every slight flexing of Earth's solid body in response to the moon's gravity. To understand where this process leads, where this long journey ends, we must follow the mathematical trail of orbital evolution into the deep future. As Earth rotates, completing each 24-hour cycle, the tidal bulges created by the moon's gravity are carried slightly ahead of the moon's position by Earth's rotation. This misalignment of just a few degrees creates a gravitational pull on the moon that has a forward component, pulling it along in its orbit, transferring angular momentum from Earth's spin to the moon's orbital motion. This transfer gives the moon extra energy, which manifests as an increase in orbital distance. Meanwhile, Earth's rotation slows because angular momentum is conserved in the system. What the Moon gains, Earth must lose. Dr. James O'Donoghue, a planetary scientist who has worked extensively with NASA studying the dynamics of rotating bodies in the solar system, explains this elegant exchange with beautiful simplicity. It is like a cosmic seesaw, he says. Earth gives away rotation, loses spin, lengthens its day. The Moon takes distance, moves farther away, lengthens its orbital period. Both bodies are heading toward an equilibrium, a balance point, a final configuration where the exchange can cease because there is nothing left to transfer. That equilibrium point, that ultimate destination, has a precise name in the language of celestial mechanics. Scientists call it mutual tidal locking. It describes a state where both bodies, both Earth and Moon, rotate at exactly the same rate, completing one full turn in the same amount of time. In this configuration, Earth's day, the time it takes for our planet to complete one rotation, becomes exactly equal to the Moon's orbital period, the time it takes for the Moon to circle Earth once. At that distant moment, one hemisphere of Earth will permanently face the Moon, seeing it forever in the sky, while the other hemisphere will never see it at all, existing in a perpetual absence of moonlight. Using sophisticated orbital dynamics models developed by NASA and other space agencies, models that incorporate general relativity and account for tiny perturbations from the Sun and planets, scientists have attempted to estimate when this mutual locking might occur. The calculations are challenging because they require projecting the system's evolution billions of years into the future, accounting for changes in tidal dissipation rates as the Moon moves farther away, considering the gradual increase in the Sun's luminosity as it ages, and dealing with other subtle effects. The best current estimate suggests mutual locking could occur somewhere around 50 billion years from now, give or take tens of billions of years depending on exact parameters that are difficult to constrain. But here is the remarkable thing, the twist in this cosmic tale. 50 billion years is far longer than the remaining lifetime of the Sun. Our star, currently in the middle-aged phase of its existence, will exhaust its core hydrogen fuel in approximately 5 billion years. When that happens, the Sun will begin fusing hydrogen in a shell around an inert helium core, causing it to expand dramatically. It will swell into a red giant, its outer layers reaching outward, possibly far enough to engulf Mercury and Venus, and perhaps even threatening Earth's orbit. Long before the Earth-Moon system could achieve mutual tidal locking, both worlds will be transformed or destroyed by the Sun's evolution into a vastly different type of star. But let us set aside the Sun's interference for a moment and imagine a thought experiment. Suppose the Sun remains stable forever, neither growing brighter nor expanding. Suppose the solar system continued in its current configuration indefinitely. In that scenario, purely as an isolated gravitational system with no external interference, the Earth-Moon pair would indeed continue evolving toward mutual lock until equilibrium was finally reached. The process is inexorable, driven by physics that cannot be stopped as long as tidal friction exists. At that hypothetical equilibrium point, a single day on Earth would last approximately 47 current Earth days. That is how long it would take for our planet to complete one rotation on its axis. The Moon, orbiting at whatever distance corresponds to that orbital period through Kepler's laws, would take exactly the same 47 days to complete one orbit. The mathematics of orbital mechanics dictates this correspondence. For a given orbital period, there is exactly one orbital distance that satisfies the equations. For the Earth-Moon system to be mutually locked with a 47-day period, the Moon would need to be at roughly 550,000 kilometers from Earth, significantly farther than its current 384,000 kilometers. At that moment of perfect balance, the tides would stop flowing. The ocean's ancient rhythm, the twice-daily rise and fall that has shaped coastlines and influenced life for billions of years, would cease. The water would settle into a static configuration, bulge slightly toward and away from the Moon, but no longer moving. The energy exchange between the two bodies would end because the torque that drives it, the angular offset between Earth's rotation and the Moon's orbital position would disappear completely. Everything would slow to a standstill, at least in terms of tidal evolution. For a brief moment in cosmic time, perhaps lasting millions or tens of millions of years, the system would remain in this perfectly balanced state. But even balance in the vast arena of space does not last forever. New forces, previously negligible, would begin to dominate. As NASA's Solar and Planetary Dynamics Division explains in their technical publications, as the Sun continues its long evolutionary journey, its gradually increasing luminosity and the radiation pressure it exerts on planets will alter orbital dynamics in subtle but cumulative ways. The Sun also loses mass continuously through stellar winds, particles streaming outward from its surface at high speed. As the Sun loses mass, its gravitational pull weakens ever so slightly, and the orbits of all planets expand to compensate. The Sun's own tidal effects on Earth, though tiny compared to the Moon's effects today, would eventually become significant when Earth's rotation has slowed enough. Solar tides, currently dwarfed by lunar tides, would begin to play a role in the system's evolution. These solar tides could potentially speed up Earth's rotation slightly again, disrupting the mutual lock and sending the system into a new phase of evolution. But all of these considerations are academic because long before any of this happens, the Sun's transformation into a red giant will intervene dramatically. When the Sun becomes a red giant approximately 5 billion years from now, its outer atmosphere may expand far enough to reach Earth's current orbit. Some models suggest Earth itself might be engulfed, vaporized in the outer layers of the bloated star. Even if Earth survives by moving into a slightly higher orbit as the Sun loses mass, the intense heat and radiation would certainly sterilize the surface, boil away the oceans, and perhaps even strip away the atmosphere entirely. The Moon, exposed to the same conditions, would be baked and bombarded. If somehow the Earth-Moon system survives this transformation, perhaps by moving far enough outward to escape the worst of the heating, the pair might continue their slow dance in the dimmer outer regions of the expanding Sun's habitable zone. They would drift together toward mutual lock as they approach the expanding red giant's illuminated edge, two barren, dead worlds still gravitationally bound, still exchanging tidal talks, still following the inexorable mathematics of orbital mechanics. When the Sun finally exhausts its helium fuel and collapses into a white dwarf, a small, dense ember radiating away its remaining heat over trillions of years, Earth and Moon might persist as a locked pair, orbiting that fading remnant, monuments to a system that once teemed with life. But the odds of this scenario are highly uncertain. The Sun's evolution involves complex interactions between its core, envelope, and outer layers. Mass loss rates are difficult to predict precisely. Exactly how far the red giant phase will extend outward depends on models that have significant uncertainties. Some simulations suggest Earth will be consumed, others suggest it will survive in an expanded orbit. The truth lies somewhere in these predictions, waiting to be revealed billions of years hence. What we can say with confidence is this: the Moon will not crash into Earth. There is no mechanism that would cause it to spiral inward under normal circumstances. Tidal friction always acts to move satellites outward when they orbit faster than the planet rotates beneath them. Since the Moon orbits roughly once per month, while Earth rotates once per day, the Moon is rotating faster in orbital terms, and tidal torques push it away rather than pulling it closer. The Moon will not escape entirely either. To break free from Earth's gravitational grasp, the Moon would need to exceed escape velocity, which at its current distance is approximately 5,800 km per hour relative to Earth. No known natural mechanism within the Earth-Moon system could provide anywhere near that much energy. The gradual outward drift caused by tidal friction will never accelerate to escape velocity because the forces responsible for that drift weaken too rapidly as distance increases. At greater distances, tidal forces become exponentially weaker, following the inverse sixth power of distance. The drift slows down as the Moon moves away. Instead, what is far more probable, what physics and mathematics strongly suggest, is a kind of eternal companionship between Earth and Moon. Over billions of years, the Moon will circle farther and farther away, its orbit widening gradually until it settles into a stable mutual lock with a slowly rotating Earth. If external factors, like the Sun's evolution, do not intervene, this locked state could persist essentially forever, stable against any small perturbations, an equilibrium reached after 4.5 billion years of gravitational evolution. Then the view from the Moon, if any observer could somehow exist there to witness it, would change in a profound way. Earth would stop its slow rise and set in the lunar sky. Currently, for an observer standing at the centre of the Moon's near side, Earth appears to hang nearly motionless, but there is slight apparent motion due to libration. When mutual lock is achieved, even that small motion will cease. Earth will become a perfectly stationary object in the sky, a blue and white sphere, perhaps by then grey and dead, suspended forever at the same point above the horizon, never moving, never changing position. From Earth's surface, the transformation would be equally profound. For half the planet, the lunar hemisphere as it might be called, the Moon would be permanently overhead, moving neither east to west nor north to south. It would be frozen in position like a painted decoration on the sky. Cities and continents on that hemisphere would have the Moon always visible, never experiencing moonless nights, though the phases would still cycle as the Moon orbits the Sun along with Earth. The Sun's illumination angle would change, creating the familiar sequence of new moon, crescent, quarter, gibbous, full, and back again, but the Moon's position in the sky would remain fixed throughout all these phases. For the other half of the planet, the anti-lunar hemisphere, the change would be even more dramatic. The Moon would never appear, not at moonrise, not at moonset, never. That entire hemisphere would exist in a permanent state without ever seeing the Moon. The familiar rhythm of waxing and waning, of full moons and crescent moons, of bright nights and dark nights, would simply not exist. The sky would contain only stars and sun and planets, lacking the companion that has shared human history since our species first leapt upward. The cultural and psychological impact of such a change, were there any humans still existing to experience it, would be enormous. Societies and religions and myths have been built around the Moon for all of human existence. The loss of Moon visibility for half the planet would fundamentally alter human connection to the cosmos. Cities that never see the Moon would develop entirely different cultural narratives. The very concept of months, originally based on lunar cycles, would become meaningless on the moonless hemisphere. But of course, no humans will likely exist billions of years from now when this transition occurs. Life on Earth will have ceased long before, ended by the Sun's gradual brightening and eventual red giant phase. The Earth-Moon system's journey toward mutual lock will proceed without witnesses, without observers, carrying out its mathematical destiny in silence. Dr. Neil deGrasse Tyson, in one of his lectures on cosmic evolution, describes such far future scenarios as the universe settling into stillness, not death but equilibrium. That stillness is not lifeless in a negative sense, he explains. It is simply the natural conclusion of motion, the balance that is reached after a long, long period of energy exchange between celestial bodies. Every system in the cosmos, from the grandest galaxy cluster to the smallest atom, eventually moves toward equilibrium states. The Earth-Moon pair follows this same universal principle, drifting gradually toward a configuration where no further change is possible, where all the available energy has been dissipated, where motion has resolved into the most stable form possible given the constraints of angular momentum and gravity. At that far distant time, if by some miracle any observers still existed on what remained of Earth, they would witness something truly remarkable. They would see a moon locked forever above the same horizon, never rising or setting. The same craters, the same ancient Maria formed billions of years earlier, the same mountains and valleys, all frozen in exactly the same orientation, visible in the same part of the sky, unchanging across years and centuries and millennia. It would represent the ultimate calm, the absolute end of tides, the complete cessation of rotational evolution between two worlds locked eternally in gravitational embrace. And perhaps in that profound stillness, in that ultimate state of equilibrium, there would be a kind of beauty. Perhaps that calm would reveal something we often forget in our busy, changing, dynamic world. Perhaps it would show us that what appears motionless is simply the endpoint of motion perfected, the destination toward which all systems naturally evolve. The moon's stillness is not absence of change, it is completion of it. It is the final word in a story written across billions of years in the language of gravity and angular momentum. As NASA scientists often remind us when discussing these deep time scenarios, stillness in space is never truly absolute. It is merely balance achieved, equilibrium reached, a temporary way station in the vast unfolding of cosmic time. The Earth-Moon system's mutual lock, if achieved, would represent such a way station, stable for an era, but eventually subject to disruption by external forces, by the sun's death, by the collision with another galaxy in the far future, by events we cannot even imagine from our present vantage point. So will the moon ever stop facing Earth? The answer, surprisingly, is yes, but only when Earth itself has slowed enough to face the moon back. Two worlds locked together in perfect synchrony, unmoving relative to each other, orbiting the sun as a single unit. When that day arrives, if it ever does, a day will last as long as a month. The tides will sleep their eternal sleep. The sky will stand still. Time itself will seem to pause in the dance between these two ancient companions. And when that moment of ultimate balance comes to pass, perhaps the most accurate way to describe the situation, the truest way to capture the essence of what has happened, would be this simple observation. We have always called the moon still, motionless, locked. But maybe, just maybe, it has really been the Earth that was slowly falling asleep all along, gradually slowing its own rotation until it could finally rest in the same stillness it forced upon its lunar companion billions of years ago. If this quiet journey through the night and through deep time has brought you even a small moment of calm, even a brief respite from the noise of everyday existence, I am deeply grateful that you have chosen to share it here with me in this space. A gentle like or a soft tap on that subscribe button is not just support in some abstract sense. It is what allows me to continue crafting these night voyages into the intersection of science and silence, these explorations where learning becomes meditation and knowledge becomes peace. And if you would like to, if you feel moved to do so, I would love to know where you are listening from. Which corner of this still spinning world holds your night right now? Which time zone contains your moment of quiet? Your words in the comments, whether they are short or long, detailed or simple, are like tiny lights scattered across this vast universe we share. Each one reaches across the darkness to remind me that somewhere, someone is listening, learning, perhaps finding the same wonder I feel when contemplating these cosmic mysteries. And I read everyone with care, with attention, with gratitude, until we meet again under another quiet sky, under another phase of that ancient moon still showing us good night, and may your dreams be as peaceful as the moon's eternal gaze upon our earth.